fact, if an industry or if, say, as an algorithm designer, we are not learning from our failures. So now a quick story from the black box thinking book, because this is going to highlight the black box style of investigation which has influenced me a lot in designing the unified differential evolution algorithm. Now this is a story on the losses of bomber aircraft during World War II, and it was conducted by one of the most brilliant mathematicians of the 20th century named Abraham Wald. Now, few investigations in the entire history have been as ingenious as that conducted by Wald. And his work was classified for decades, but the full story and how it contributed to the defeat of Nazism has recently been told. Now, during World War II, Wald was asked by military to help them with a crucial issue. Now, bomber aircrafts which were deployed in Europe uh, by America were being asked to take huge risks. For certain periods of the conflict, the probability of a pilot surviving a tour of duty was little better than 50-50. So there were a lot of crashes. Now, the wartime leaders realized that they needed to reinforce the planes with armor. Now, this would help protect them from gunfire from the ground and the air. The problem is that they could not armor the entire surface area because that would make the planes too heavy to fly and the planes would lose agility. And Wald was brought in to prioritize the areas that needed armor the most. And he had lots of data to work from. And just imagine, we are talking about World War II, right? So around like late 1930s, 1940s. And at that point also, Abraham Wald had lots of data to work from. And to their credit, the Air Force had taken the trouble to examine returning aircraft to assess the extent of the damage and how they might respond to it. And this is typical black box style behavior. They were examining the data from adverse events in order to work out how to improve the safety of these bomber aircrafts. Now, to the relief of the Air Force Command, the pattern seemed clear. Many of the planes were riddled with gunfire all over the wings and the fuselage, but they were not being hit in the cockpit or the tail. And the longer the incident reporting continued, the clearer the pattern became. And this is how the pattern looks like. And again, this is from the same book, which is Black Box Thinking. So this is a bullet-free airplane, and this is the figure which shows the bullet hole locations in the returning airplanes. And we can see that there are holes because of the bullets all across the airplane, but not at the cockpit and the tail. Now, the military command came up with what seemed like the perfect plan. They would place armor on the areas of the plane where there were holes. This is where the bullets were impacting and therefore where the planes needed additional protection. It was plain common sense. But Wald disagreed. He realized that the chiefs had neglected to take into account some key data. They were only considering the planes that had returned, and they were not taking into account the planes that had not returned, i.e., the planes that had been shot down. The observable bullet holes suggested that the area around the cockpit and tail didn't need reinforcing because it was never hit. In fact, the planes that were hit in these places were crashing because this is where they were most vulnerable. In effect, the holes in the returning aircraft represented areas where a bomber could take damage and still return home safely. They had survived precisely because they had not been hit in the cockpit and the tail. So the pattern of holes, far from indicating where the armor needed to be added to the aircraft, was actually revealing, on the contrary, the areas where it did not need the armor. So this insight turned out to be of profound importance, not just to the bomber command, but to the entire war effort. Wald's analysis of bullet-riddled aircraft in World War II saved the lives of dozens of brave airmen. And this is a powerful example because it reveals a couple of key things. The first is that you have to take into account all the data and all the information, including the information or the data that you cannot immediately see. It also emphasizes that learning from failure is not always easy because the failures are not always obvious, and even the information which the failure shows us is not always easy to interpret. So, the failure, learning from failure is not easy even in conceptual terms, let alone emotional terms. And it takes careful thought and a willingness to pierce through the surface assumptions. And often it means looking beyond the obvious data to glimpse the underlying lessons. And this is not just true of learning in aviation, but in every field. And like I'm in a way very glad to share that this is the kind of black box style investigation which I have applied throughout my whole journey when I have been designing the unified differential evolution variants, and I'll be sharing this in more detail as we go on. So now let's move on to how we designed unified differential evolution 1, which was in 2017. So now let's come back again to unified algorithm design. As discussed earlier, unified algorithm design involves focusing on all the design elements of the algorithm. So the first step was to identify what are the design elements of DE. To do so, we reviewed many state-of-the-art papers on DE and the survey papers. And here I have listed two of the most survey papers. Both are by Professor Swagatam Das and Professor Suganthan. In fact, I'm aware that Professor Swagatam Das is going to be the next speaker today evening. So if you want to learn more about DE, please go and look at these survey papers. And now let's move on to the design elements of DE. To those who are already working in the field of D, you might be knowing, but let me still share. The original D algorithm was proposed by Stone and Price in mid 1990s, and this is the first technical report on D by Stone and Price. Now, D is a simple yet powerful evolution algorithm for real parameter optimization. And D is different from traditional EAs in the sense that it perturbs the current generation population members with the scale differences of randomly selected and distinct population members. Now, I'm not going to present the equations for the differential evolution variants and so on because I'm aware that there was a separate talk on D. So I hope like many of you must have attended the talk. But even if you have not attended and you are not aware, I think knowing these equations of D is not that much important with respect to this talk. So overall, several classical D variants were proposed such as D, Rand1, D, best one, etc. Now, the classical D variants were very simple in design. They consist of a single mutation strategy which is used throughout the evolution. And they used control parameters F and CR. So F is the parameter related to the mutation, and CR is the crossover rate. These control parameters also remain fixed throughout the evolution in the classical D variants. But over the years, a lot of new ideas were proposed and a lot of new design elements came up in the field of DE. One of that is the mutation strategy itself, because researchers proposed novel mutation strategies. Then the researchers went a step further and they proposed a pool of different mutation strategies. They also proposed strategy adaptation for this pool of strategies, that how the strategies can be adapted as the evolution progresses. Then researchers also proposed pool of parameters. They also proposed parameter adaptation, that is how these parameters, control parameters, can be adapted in an online manner. And for constraint optimization problems, constraint handling itself is a design element. Now, under the pillar of unified algorithm design, our intention was to pay attention to all of the above design elements. Definitely, in the first version, we didn't or we couldn't pay attention to all the design elements, but later on, in the subsequent versions, we paid attention to all these design elements. In fact, we also came up with more design elements and integrated that. And I'll be sharing all of that. So now let's move on to how we applied offline learning to design UDE. Now, offline learning, as discussed earlier, involves studying relevant high performing algorithms and taking inspiration from them. But instead of randomly studying the high performing D algorithms, we focused on each design element of DE, the design elements which I showed in the previous slide, and we studied the high quality algorithms proposed corresponding to each of these design elements. So now let's take a look at what was our offline learning with respect to mutation strategy. Now, in 2009, Zhang and Anderson proposed a D variant named Jade, and this is the reference, and it has received like more than 3,900 citations. Now, one of the key features of Jade is the mutation strategy named DE current to P best 1. Now, instead of utilizing only the best vector in mutation as done in DE current to best 1, DE current to P best 1 utilizes the top P best vectors in mutation. So, uh, when I say offline learning, what we were doing was we were looking at the high performing algorithms across each of the design elements, and this was the high performing algorithm we looked, or maybe in the end we selected. We definitely looked at many other algorithms, but we selected this one. Then coming to offline learning with respect to the mutation strategy pool, in 2011, Wang et al. Proposed an algorithm named CODE, or composite differential evolution. In fact, this algorithm is also like very popular. And one of the main features of CODE is to use a pool of mutation strategies at each iteration. That is a strategy pool. And the strategy pool in CODE consists of three strategies, which are D rand1 with the binomial crossover, D rand2 bin, and D current to rand1. So these are the three strategies in the strategy pool. But like which strategies go into the strategy pool is itself an important design element. Now coming to offline learning with respect to parameter pool. So parameter pool is actually not a very popular design element because this was later replaced by parameter adaptation. But since the first version of our UDE still included parameter pool, and that is why I'm discussing this. Now this I have already mentioned that in the original D algorithm, F and CR used to remain fixed. However, later it became well known that single parameter setting may not be the best throughout the evolution. Hence, in code, the authors proposed using a parameter pool, and the parameter pool consists of three different control parameter settings, which are shown here. So these are three different combinations of F and CR. Next, coming to offline learning with respect to parameter adaptation, because later on we replaced parameter pool with parameter adaptation. So let me share our offline learning with respect to parameter adaptation as well. So as I mentioned, a parameter pool like the one used in code has only three different combinations of F and CR. The researchers have proposed different parameter adaptation strategies to adapt F and CR in a more holistic manner throughout the evolution. And SHADE, which is the success history based parameter adaptation for D, proposed by Ryoji, Tanabe, and Alex for unconstrained optimization problem. This is one of the most famous algorithm for parameter adaptation in D. I'm not saying there are not others. There are many others definitely, but Shade is also one of the very popular algorithm. And Shade had won the competition in 2013 for the unconstrained optimization problems category. Then coming to offline learning with respect to strategy adaptation. Now again, as I mentioned, the D mutation strategies in the classical D variants remain fixed. However, in 2009, so this, if I'm not wrong, is one of the first algorithms, D algorithms, to propose strategy adaptation in D. And this algorithm is called SADE, or self-adaptive differential evolution. There is a reference. Now the strategy pool in SADE consists of four different strategies, which are D rand1, rand2, current to rand1, and rand2 best 2. Now, the characteristic feature of SADE lies in the gradual self-adaptation of the probabilities corresponding to both mutation strategies as well as their associated parameter values by learning from their experiences of generating promising solutions within a certain number of previous generations, which is called the learning period. So this is the characteristic feature. So now let's come to UDE1, which I developed for the CEC 2017 competition. Now, having identified the different design elements of D and having learned from some of the high performing D algorithms proposed along different design elements, what we had to do was that we had to find a way to bring our learning together. And that is to take as much inspiration from the different high performing D algorithms proposed along different design elements and find a way to stitch these ideas together, and also at the same time not just stitching these ideas as they were proposed, but making improvements in those ideas by addressing their weaknesses under a single algorithm. So this, as I mentioned, this was published in the CEC 2017 conference. Now, to bring all these ideas together, I was looking for a skeleton algorithm, right, or for a framework, and that is when I, like having already known about code, I chose code as the backbone or the skeleton of DE. So I was particularly impressed by this algorithm code, which I've already described. It uses a pool of three mutation strategies and a pool of three control parameter settings. And code combines them randomly to generate three trial vectors corresponding to each target vector. So this is how it works. So see, this is a target vector I at tth generation. So since it uses three different trial vector generation strategies, it uses them on this target vector and creates three different trial vectors, which are shown here. Then it selects the best trial vector from these three trial vectors, which is shown here. And then finally, this trial vector is compared with the target vector, and the better vector goes on to the next generation. So this is how the strategy pool and the parameter pool, right, in this whole framework of code works. So it's actually a very simple framework. And as I've already mentioned, this is the strategy pool of code. This is the parameter pool. Now let's come to the black box thinking, because this is what I applied to design UDE. So I started with code and I started applying black box thinking or the black box style investigation to code. So as discussed earlier, black box thinking involves determining the weaknesses of an algorithm and then addressing those weaknesses. So we studied this algorithm code in detail and determined its several weaknesses. So the first weakness is that code uses three mutation strategies corresponding to each target vector and creates three trial vectors corresponding to each target vector. So we realize that this methodology is actually computationally very inefficient, because say if we have a population size of 100, at every generation code is creating 300 trial vectors, right? So it is consuming three times the function evaluations as compared to any other D. So that was the first weakness. The second weakness was that the strategy pool in code consists of D rand1, rand2, and current to rand1 mutation strategies. And we realized the weakness that none of the mutation strategy in this pool exploits the best vector or the best vectors. So we realize that the exploitation strength of the strategy pool is quite low, and that is a weakness. Then the third weakness is that code uses a strategy pool and a parameter pool, and it combines them randomly to generate trial vectors. So the weakness of code is that it does not use any strategy adaptation or any parameter adaptation. In other words, there is no online learning in code. So these were the three weaknesses. To summarize, it's a computationally inefficient framework. The best vectors are not used in the strategy pool, and there is no online learning. And that is when we started applying the black box thinking to design UDE. So to target the different weaknesses in code, we came up with different ideas. And broadly speaking, these ideas were actually targeting all of these different weaknesses. The first idea was a dual population approach so as to make the framework more computationally efficient as compared to code. The second idea was to introduce a trial vector generation strategy based on the best vector or best vectors to promote exploitation. The third idea was to introduce strategy adaptation and apply online learning, which was missing in code. So eventually, this is how the strategy pool of UDE1 looks like. There is D rand1 and D rand2, which were also there in code. But then we replaced D current to rand1 with the strategy D current to P best one, which was originally proposed in Jade, because this can exploit the top P best vectors and has a more exploitation strength. Next, the parameter pool, we didn't make actually any innovation here. we just reduced from 3 control parameter settings in code to 2 control parameter settings. So these are the 2 control parameter settings. And then at each generation, UDE1, what it does is that it divides the population into 2 equal size subpopulation. So you can imagine a top subpopulation and a bottom subpopulation. In the top subpopulation, UDE1 employs all the 3 mutation strategies, just like in code. But in the bottom subpopulation, to make the framework more computationally efficient and to also deploy strategy adaptation, what UDE1 does is that it employs strategy adaptation based upon how the 3 mutation strategies perform in the top subpopulation in the previous learning period. So overall, we introduced a dual population approach to make the algorithm more computationally efficient. We made this modification in the strategy pool, and we introduced the strategy adaptation. The constraint handling, for that, UDE1 employs a simple static penalty method to handle the constraints. It employs a generational style replacement method like in traditional GA, and it also employs a local search method as well. Now, I won't go into the results of UDE1 because later on UDE2 and UDE3 performed even better. So I will be sharing the results later on. But as discussed earlier, UDE1 went on to secure second rank in the CEC 2017 competition. And this performance gave me the preliminary validation of my design philosophy. However, UDE1 was designed in just 4 months' time, and I knew it had several limitations and could be improved significantly. So that is where we move on to the CEC 2018 competition. So CEC 2018 competition actually repeated all the same problems from CEC 2017 competition. So 28 benchmark problems across the 4 different dimensions. So now let's take a look at how we designed UDE2. So again, to design UDE2, I used the black box thinking. So we identified the different weaknesses of UDE1, and there were several weaknesses. First weakness was that the constraint handling method in UDE1 was based on the static penalty function method, and it is well known that the static penalty function method has several limitations. And in 2018, I could not like submit a paper to the conference itself because the conference was held in Brazil, and at that time I was not able to attend the conference. So I participated in this conference by submitting a technical report, which is also allowed, and this is the reference. The Now coming to the second weakness of UDE1, the second weakness is that UDE1 uses a parameter pool with just 2 control parameter settings, which may not be ideal. And what UDE1 lacked is parameter adaptation. The third weakness is that UDE1 utilized generational replacement method, but D-based methods mostly employ one-to-one replacement method. And the reason for which I first introduced generation replacement method is because during my PhD, I had worked a lot on GA, and that is why I first brought in the generational replacement method. But later on, I replaced it with the one-to-one replacement method of D. And the fourth weakness was that the local search method incorporated in UDE was not a good method. It does not mean local search cannot or should not be integrated in UDE. It rather means because of our inexperience with the local search methods, we were not able to integrate a suitable local search method. So now to target these different weaknesses in UDE, we came up with different ideas. Broadly speaking, the ideas were removal of the local search operation because it was not performing well, substitution of the generational replacement technique with one-to-one replacement, and introduction of sophisticated parameter adaptation technique, and introduction of powerful constraint handling technique. So these were the main ideas. So again, I went to the offline learning because when I had to introduce parameter adaptation, I looked at what interesting ideas had already been proposed in the literature. So now we were aware we had to replace the parameter pool with a parameter adaptation technique. So we reviewed relevant high performing algorithms, and we came across Shade, which I've already mentioned earlier. This is the winner of the 2013 competition on the unconstrained problems. So Shade looked promising, but the challenge was that it was originally proposed for the unconstrained optimization problems, and we were designing UDE for the constrained optimization problems. Now, one idea could have been that we could have done research on modifying Shade to apply to constrained optimization problems. However, that in itself could have been a research direction on its own. So we started finding out if anyone had modified shade and applied it to constraint optimization problems. And that is when we came across L shade 44, which extends the shade for solving constraint optimization problems. And L shade was proposed in 2017. So this is one idea that when you are designing, say, a new algorithm, you should not be just looking at the state of the art algorithms which have been proposed in the past. You should also be very much aware of the current literature. So when I was designing UDE2 in 2018, L Shade 44 was just published in 2017, and I paid attention to this algorithm. So we reviewed this in detail and integrated it into UDE2. So it is noted that the integration of a strong parameter adaptation method in UDE2 is also aligned with the online learning pillar of my design philosophy, because this is based on the parameter adaptation. So now offline learning with respect to the constraint handling technique. Next, we wanted to replace the static penalty function method in UDE. And the literature on constraint handling techniques is actually very vast. So the challenge was to find out a strong constraint handling technique and integrate it effectively into UDE2. So our literature survey led us to Code Square. So this is what I call Code Square, which is the extension of the original algorithm code to solve constraint optimization problems. And this is the reference. And in fact, it was published in 2018. So again, I was very much aware of what was happening in the literature at that point of time. The characteristic feature of constraint handling technique in Code Square lies in the hybridization of two different popular constraint handling techniques. Specifically, it is a combination of superiority of feasible solutions method and the constraint handling method, epsilon constraint method. So this is how this constraint handling technique works. So again, on a target vector, three different mutation strategies are applied to create three trial vectors. Then in the first selection, where the best of these three trial vectors is selected, the feasibility rule is chosen. And then when we have to compare this best trial vector with the target vector, the epsilon constraint method is chosen as the constraint handling technique. Since UDE2 is a dual population based algorithm like UDE1, and the top subpopulation has a structure similar to code and code square, in UDE2, the top subpopulation employs a combination of these two constraint handling techniques, just like in code square. However, since bottom subpopulation generates only one trial vector, it employs only the epsilon constraint method. So what we were doing were we were looking at the interesting ideas which had been proposed in the literature, but we were also kind of adapting them or making modifications to integrate them into our framework. And we were also looking at their weaknesses and how we could address those weaknesses. So let's take a look at some of the results on the 30D problems. So here on the leftmost column, we have these 28 problems. Then we have compared UDE2 with UDE, and these are the mean and the standard deviation results of 25 runs on each problem. So the best results are shaded in gray here. So here we can see that UDE2 performed better than UDE on 21 problems. It performed worse on 5 problems and performed similar on 2 problems. But overall, we can see that UDE2 improved significantly and it performed better on 21 out of 28 problems. So that was a remarkable improvement. So next, let me quickly move on to the 2024 competition, which was held just last year, and how we designed UDE3. So again, the trend continued. To design UDE3, we applied black box style investigation to UDE2. We identified the weaknesses of UDE2. We figured out several weaknesses. The weakness one was that in both the earlier versions, we assumed, in fact, we randomly assumed the size of the top subpopulation and the bottom subpopulation to be the same. However, the size of the subpopulations can also have a significant impact on the performance of the algorithm. So that was the first weakness. So again, just to highlight that in 2024 as well, we participated in the competition by submitting a technical report. And this technical report is available on archive. And I'll be sharing the slides later and you can look at the paper also. The second weakness is that we observed that the strategy adaptation method in UDE1 as well as UDE2 considered only the number of wins of the mutation strategy while determining the adaptive probability. But this is a mistake, because when we determine this adaptive probability, we have to take a look at not just the number of wins, but also the number of losses in the learning period. Additionally, we observed that the strategy adaptation was taken into consideration only with respect to the performance of the mutation strategies in the top subpopulation, and it was ignoring rich information that could be exploited by taking into account the bottom subpopulation as well. Then the third weakness is that our experimental investigations indicated that there is a parameter CP in the epsilon constraint method, and it was taking like very large values on some problems, and because of that, the performance of the algorithm was quite bad on some of the problems. And the fourth weakness was that it was actually not obviously evident from the algorithm. So to further identify the weaknesses of UDE2, we delved deeper into the literature of DE, and we learned that stagnation is a common issue in many DE algorithms. Stagnation means that during the evolution of DE, many individuals get stuck, and despite allocation of computational resources, they may not improve. And we analyzed our algorithm and observed that stagnation was indeed happening on several problems. Now, to target the different weaknesses in UDE2, we again came up with different ideas. Broadly speaking, these ideas were considering the size of the two subpopulations as a parameter, enhancement of the strategy adaptation method, fine tuning of the parameter CP in the constraint handling technique, and introduction of a novel strategy to overcome stagnation. Now, we extensively experimented with the size of the subpopulations and observed that it is indeed an important design element. And our experimental investigation demonstrated that the size of the top subpopulation equal to 25% of the population size, and the size of the bottom subpopulation equal to 75% of the population size works the best. Next, coming to the strategy adaptation in UDE3, to overcome the shortcomings of the strategy adaptation in UDE2, we took the following two measures. First, for determining the adaptive probability of each mutation strategy in the bottom subpopulation, we recorded and utilized not only the number of wins, but also the number of losses of each mutation strategy in the learning period. So this is something which was done originally in the algorithm SAID as well, but unfortunately we had missed out on this. And so again, as we discussed earlier, sometimes the failures can be like very subtle, right? And it's only upon closer observations that we can find out these failures or these weaknesses. Secondly, this information was recorded over the entire population instead of just the top subpopulation, like in the previous two variants of UDE2, UDE1 and UDE2. So now coming to the constraint handling technique in UDE3, to address the negative impact of the large values of the parameter CP, we experimented by setting different upper threshold limits for CP, and we observed that the upper threshold limit of 33 works the best across all the problems. So this is the simple condition that we set on CP. Then coming to this novel stagnation strategy which we proposed in UDE3, to integrate a strategy to overcome stagnation, we again studied several strategies presented in the literature. However, the research works focused on stagnation are not that many. So I believe it is still a very niche area. But we learned about the general ideas, but we did not find a strategy good enough to directly integrate. And that is when we decided to design our own stagnation strategy. Now, the research works in literature on the stagnation strategy in general focus on finding a stagnated individual and then replacing it with another individual. So we delved deeper into this and determined three key design elements to be focused on when designing a stagnation strategy. And let's look at the three design elements. First, when can an individual be said to be stagnated? Generally, if an individual has not been replaced by its trial vector for many generations, it is said to be stagnated. So we used a parameter SG, which indicates the number of generations for which, if an individual has not shown improvement, it can be said to be stagnated. Second, should a stagnated individual be immediately replaced, or should the stagnation strategy be applied if a certain proportion of the population stagnates? We researched this extensively and observed that replacing a stagnated individual immediately does not result in consistent superior performance. Hence, we introduced a parameter S prop to indicate the threshold for the proportion of the stagnated population beyond which the stagnation strategy is activated. See, if the S prop is 50%, the stagnation strategy gets activated only when the 50% of the population members are already stagnated. Third, the choice of an incoming individual which replaces a stagnated individual is very important. And it is important that the incoming individual is a high quality individual so that there can be a good chance to replace the stagnated individual. And as we discussed earlier, EAs generate a lot of data, a lot of information during the evolution, and many times these are not exploited. So to address this challenge of having high quality individual incoming individuals to replace the stagnated individuals, we applied online learning, and UDE3 maintains an external archive of size NP, which is same as the population size, to store the unsuccessful trial vectors generated during the evolution. So generally in the literature on D, these unsuccessful trial vectors are just ignored. But UDE3 maintains an archive of these unsuccessful trial vectors. This archive is updated at every generation, and the size of the archive is always maintained to be less than equal to the population size using the superiority of feasibility principle. And once the proportion of the stagnated population is greater than the S prop of NP, one stagnated individual is replaced at every generation with a randomly selected vector from the external archive. So this way, UDE3 effectively utilizes the large number of unsuccessful trial vectors in the stagnation strategy. Now, finally coming to the parameter settings in UDE3, the population size taken was 100. So one thing which I forgot to mention about 2024 problems was that only 30 dimension problems were considered, 30D, and the metric not only looked at the final quality of the result, it also looked at the speed at which the algorithm was able to obtain the high quality results. So both speed and accuracy was checked. The size of the top subpopulation is 25. Learning period is 25 generations. SG is 35 and S prop, as I mentioned, is 50%. So now let's take a look at the effectiveness of the stagnation strategy on the problem F7. So here this graph on x-axis, it shows the number of iterations which goes on till 4000. And on y-axis, we have the average distance of the population to the centroid. And here we have the results of two algorithms. The red one is with stagnation or with replacement, so this red curve, and the blue curve is without stagnation. So as we can see, without the stagnation strategy, there is stagnation, in fact, significant stagnation in the algorithm, because the average distance of population of the centroid is very large. In contrast, with the introduction of the stagnation strategy, this average distance to centroid keeps on decreasing and it reaches 0. So next we track the number of stagnated individuals in these two variants. So we can see that without this stagnation strategy, there is a huge stagnation in the algorithm. So in fact, after or around 2000 generations, almost all 100 particles or individuals become stagnated. On the other hand, when the number of particles or stagnated particles reach 50, right, the activation, the stagnation strategy gets activated and it starts working, and it brings down the number of stagnated particles. So overall, now I do not have time to look at or show the impact of each and every design operator, but let's take a quick look at the effectiveness of dual population. So on left, we have the single population variant, which does not employ any dual population approach. And on the right hand side, we have the dual population UDE3. We can see that the dual population approach performs better on 15 out of 28 problems. Then finally, let's compare UDE3 with UDE2 on these 28 30D problems. Again, we can see that UDE3 performs better than UDE2 on 17 problems. Again, this performance has been, or the improvement in performance has been significant. And finally, let's compare UDE3 with CLSRD, which was the runner-up in this 2024 competition. And this CLSRD is an algorithm proposed by the Russian authors. And actually, the competition was like neck to neck. but UD3 slightly outperformed CLSRD. It performed better on 13 problems and worse on 11 problems, similar on 4 problems. So now a quick summary of the talk. In this talk, I covered how I designed the different versions of my award-winning algorithm, UD1, 2, and 3. I covered the main pillars of my design philosophy, which are unified algorithm design, offline learning, online learning, and black box thinking, and how these concepts were applied. And these principles are actually quite robust and universal and could be adopted to design new algorithms or improve existing algorithms. So Dr. Satya Sai ji, if I have like couple of more minutes, I would just like to end the talk in 2 more minutes. Is it okay?
Yes, sir, this is fine. You can take
Okay,
more.
sure, sure. So now let me end this talk by sharing a very interesting story on British cycling. How 1% performance improvements led to Olympic gold. So this is again a very quick story, and you can find the references here. The fate of British cycling changed one day in 2003. The organization, which was the governing body for professional cycling in Great Britain, had at that time hired Dave Brailsford as its new performance director. At that time, professional cyclists in Great Britain had endured nearly 100 years of mediocrity. Since 1908, British riders had won just a single gold medal at the Olympic Games. They had fared even worse in the cycling's biggest race, which is the Tour de France. In 110 years, no British cyclist had ever won the event, and Brailsford had been hired to put British cycling on a new trajectory. What made him different from previous coaches was his relentless commitment to a strategy that he referred to as the aggregation of marginal gains. And this is the philosophy of searching for a tiny margin of improvement in everything you do. He said the whole principle came from the idea that if you broke down everything you could think of that goes into riding a bike and then improve it by 1%, you will get a significant increase when you put all of them together. So Brailsford and his coaches began by making small adjustments you might expect from a cycling team. They redesigned the bike seats. They asked the riders to wear electrically heated over shorts. The team tested various fabrics in a wind tunnel and so on, which proved on to be lighter and more aerodynamic. But they didn't stop there. Brailsford and his team continued to find 1% improvements in overlooked and unexpected areas. They tested different types of massage gels to see which one led to the fastest muscle recovery. They hired a surgeon to teach each rider the best way to wash hands so as to reduce the chances of catching a cold. And they determined the type of pillow and mattress that led to the best night's sleep for each rider. As these and hundreds of other small improvements accumulated, the results came faster than anyone could have ever imagined. Just 5 years after Brailsford took over, the British cycling team dominated the road and track cycling events at the 2008 Olympic Games in Beijing. They won an astounding 60% of the gold medals available. 4 years later, when the Olympic Games were held in London, the Brits raised the bar as they set 9 Olympic records and 7 world records. That same year, Bradley Wiggins became the first British cyclist to win the Tour de France. The next year, his teammate Chris Froome won the race, and he would go on to win the race in 2015, 16, and 17, giving the British team 5 Tour de France victories in 6 years. During the 10-year span from 2007 to 2017, the British cyclists won 178 World Championships and 66 Olympic or Paralympic gold medals, which is unbelievable. And they captured 5 Tour de France victories in what is widely regarded as the most successful run in cycling history. Now, Dave Brailsford credits the transformation of the British cycling team to the aggregation of marginal gains. And if we take a look back at how I have designed the unified differential evolution, I have also applied or tried to apply this aggregation of marginal gains theory because I have broken down the whole framework into different design elements, and I have been trying and making progress across each of the design element and then trying to bring them together. And the result has been actually quite like satisfactory, as we saw that UD1 won the second rank in 2017, and the subsequent two versions, UD2 and UD3, won the first rank in 2018 and 2024. Not to say that I did something like Dave Brailsford, but if you have to take back something from this talk, then please remember black box thinking and disaggregation of marginal gains theory. So thank you, and then please feel free to like ask any questions.
Participants, if you have questions, just write in a chat box.
Yes, sure. I will be actually forwarding the whole deck to the organizers, and they will be sharing it with all the participants. I will also be sharing the UD3 paper, which is also available on archive. And in fact, the code of UD3 is also publicly available. So if you want to experiment with UD3, then please feel free to do so. Yeah, so thank you very much for the appreciation. I can see it like on the chat box. Yeah. Okay, if you have any queries, you can ask me later as well, and I'm sharing my email ID here. Okay, I can see one question. Can I apply to optimization problem for IMRT treatment in cancer? So, okay, I would like to share here that first of all, these algorithms have been proposed for the real parameter constrained optimization problem. So, if this IMRT treatment problem in cancer is a real parameter constrained optimization problem, then definitely you can apply it. But even if it is not, then you can still apply these design principles, which are the unified algorithm design, the offline learning, online learning, and black box thinking. So you can apply all of these design methodologies to your algorithm, and I'm sure you will see a lot of improvement in your algorithm.
So I think participants can mail their queries to you
Sure.
to the shared mail ID,
Yeah.
and the material which you will give us, we will be forward it to them.
Yeah. Sure.
On this note, thank you so much, sir, for this wonderful session.
Yeah. Thank you. Thank you so
I
much. Yeah,
think
it was my pleasure. Yeah.
such a great inspiration that has been demonstrated today. Many people will be motivated towards the research, and definitely they will be benefited from it.
Yeah, thank you so much. I can see there is one final question. Maybe I will quickly address it.
Yes, sir.
So it's from Keshav Kumar. How to design a new algorithm and how to get idea like you. So I think to do that, you have to look into the design methodology which I have shared, the design philosophy, right? So you have to look at offline learning, you have to look at online learning, you have to look at unified algorithm design. So you have to look at all the design elements of the algorithm, and you have to also look at the black box style investigation for your own problem, right? So once you do that step by step, right, and you have to kind of, as I said, you have to keep on aggregating these marginal gains, these marginal ideas, and slowly I am sure like your algorithm will improve significantly. But still, if you have any query, then please feel free to drop me an email on my email ID. Okay, I think there is some problem with the voice. I think it's fine, because I think maybe now the next speaker has to take over, and
Yes,
I think the
you are
participant.
audible, sir, to us.
Okay, great, great. Yeah, thank you so much, ma'am. Yeah.